Welcome. In the last lecture, we have seen different types of pumps and compressors. How do we classify them, and what is the principle behind all of those, and how they work? What we are going to look at now is to look at more about centrifugal pumps. So this is where we are in the course, part 4 of the course. Just to quickly revise so that you are aware of what has been covered in the past lecture, so that you are well prepared for this lecture. Just some questions. What name do we give to machines that increase pressure of a gas? How does a centrifugal pump increase pressure? Name different types of positive displacement pumps. Name different types of rotary positive displacement pumps. What could be the criteria for choosing different types of pumps? This is slightly different question. It is based on all the things that we have seen, but just to tell you what could be the criteria for choosing different. So think about this question. Answer may not be obvious based on the previous lecture, but this is something that you should be aware of. When do I choose what kind of pump? So perhaps the answers will come in this lecture and the next lecture. Okay, so here is again our centrifugal pump. This is the volute, this is the impeller. Impeller is rotating in the clockwise direction like this. Liquid comes here, liquid travels between these blades and it goes outside, and the area increases, pressure increases, velocity reduces, and we get a higher pressure of the fluid at the discharge as compared to the what is there at the suction. So what we are going to do is we are going to look at a small region between these two blades. Let's say we are going to look at this region, and the fluid is going to come from the center. Fluid is going to come from the center I. It is going to travel between these two blades, and as it is traveling, remember these blades are rotating in the clockwise direction. So if I just look at this picture as a close-up view of these blades, these are the two blades. Liquid is going to come from the center I of the impeller, and it is going to travel between these two blades, and the impeller is rotating. As a result, the liquid is going to be imparted tangential motion. So when the liquid is coming out between these two blades like this, let me just draw those arrows. So liquid is coming here, it is traveling between the blades. So if you are sitting as an observer along with the blades, you will see this motion. The fluid will take this path. But remember, fluid is coming from outside, so we are a stationary observer outside. So then the fluid is going to have two motions. One is the motion between the blades, and one the tangential motion imparted by the fluid, by the tangential motion imparted to the fluid by the impeller rotation. So now we are going to write an expression for power that is delivered by the pump to this liquid. Remember when we talked about torque, the torque was increase in tangential momentum. So we have to write a balance, you have to write a expression for how much is the increase in tangential momentum between location 2 and location 1. The increase of tangential momentum, that's the torque imparted to the fluid. Torque multiplied by 2 pi n, that's the power. That's what we are going to write an expression for. So let's say if I'm sitting with the blade, if I'm an observer with the rotating blades, fluid is going to have this kind of motion. Let's say beta is the angle that is made by the blade with this circumference. So the fluid is going to have a motion, fluid is going to have a velocity Vt if we are sitting along with the blade. That is one component of the fluid. Other component of the fluid is going to have a tangential motion. Tangential motion is, let's say, V omega. So we are going to say that these blades give perfect guidance to the fluid. Guidance mean the fluid angle at the exit is the same as the blade angle. We are going to say that the fluid is going to come out at an angle beta, right? So the fluid has one part velocity which is equal to the tangential, which is equal to the velocity Vt. It is velocity of the fluid tangent to the blade at the exit at location 2. In addition, the impeller is imparting tangential motion V omega. So V omega is nothing but tip speed, tip velocity of the impeller. It is called as V tip 2 pi n r2. Okay. Now I can do a vector sum of these two. So one component of velocity is Vt, the other component of velocity is V omega, and the resultant velocity of the fluid is in this direction V. You can see the previous video of the animation of how the impeller was rotating and how the fluid was coming out. You will notice that the fluid has a velocity in this direction. V is the resultant velocity of the fluid. We are interested in tangential momentum imparted to the liquid. So we are interested in the tangential component of this V. So this V we are going to resolve into a tangential component and a radial component. Radial means radially away from the center of the impeller. So radial component and tangential component. This component is our radial component. Okay. So this should be Vt and V omega. Let me just make that correction. So V is the resultant velocity of Vt and V omega. We are going to resolve that into a tangential component because we are interested in increase in tangential momentum of the fluid. That's a torque that the impeller is giving to the liquid. That's the increase in power of the fluid. So we are interested in the tangential component. So we are going to resolve into V theta and Vr, the perpendicular component, Vr. Okay, so now angular momentum imparted to the fluid, that is nothing but the torque. You recall from our macroscopic balances, flow rate multiplied by angular momentum per unit volume. Angular momentum per unit volume is rho into r at second 2 location exit into V theta at location 2 minus rho r at location 1, V theta at location 1. Remember what is 1 and 2. 1 is impeller where the liquid is entering, 2 is where the fluid is exiting. So in this part the tangential momentum is imparted to the fluid. Now since R1 is very small, correspondingly R1 V theta 1 is very small as compared to R2 V theta 2. So torque we are going to say is rho multiplied by Q multiplied by R2 V theta 2. And power that is imparted to the fluid is nothing but 2 pi n multiplied by the torque, and n is number of revolutions per second. So power is now going to be 2 pi n multiplied by this torque rho Q R2 V theta 2. So the head that is developed by the impeller or head that is imparted to the fluid is nothing but power divided by rho GQ. Recall from our Bernoulli equation lectures. So head that is imparted HP is nothing but 2 pi n R2 multiplied by V theta 2 rho, and then I will divide by G. Rho has cancelled out and G. And 2 pi n R2 is nothing but our tip speed, tip velocity, V tip. Okay, that's I can know that very easily. I know the speed of rotation, I know the size of the impeller. So V tip can be easily calculated. So head that is imparted is V tip multiplied by V theta 2 divided by G. Now V theta 2, look at the vector sum. V theta at location 2. This angle is beta. So this angle also is beta. This angle also is beta. So this velocity, this part of the velocity, can I write from VR? If I say tan beta would be VR divided by this. So this velocity would be, right, VR, that's here, actually it is written here, VR divided by tan beta. So VR, but it is at location 2, it is at the exit. VR2 divided by tan beta, and tan beta is also at location 2, so it is beta 2. Okay, so V theta 2 I have replaced as VR2 divided by tan beta 2. Now VR, what is VR? VR is the radial component of the velocity going away from the impeller. So if you think about this as an impeller, radial component is this, going away from the impeller. Radial component is this. So if you think about this as a circle, this is the center of the impeller. Radial component is this. Radial component is this. Radial component is this. How is it related to the flow rate? Radial component is this. Radial component is this. All such across the impeller. How is it related to flow rate? Flow rate divided by cross-sectional area. Cross-sectional area is cross-sectional area here for it to flow. That's nothing but this cross-sectional area. If I write, that's nothing but flow rate, and the cross-sectional area, if we write, it is nothing but 2 pi r2 multiplied by, let's just see what symbol I am using. I am using symbol just A, right? A tan beta 2 pi r2 multiplied by this width of the impeller. Width, let's say, is our B, some value B. So 2 pi r b2, 2 pi r2 into B. That's the cross-sectional area through which this flow rate, whatever is coming here, that's how this flow rate is going out through here. 2 pi r2 multiplied by B, width. So that we are going to call as AF, area, cross-sectional area for the fluid. AF. So, right, so let's just rub this. So VR2 I am going to replace by flow rate divided by AF, and tan beta 2 is there as such. Now can I plot this equation? This equation, what does it tell you? It tells you how much head that impeller will generate for a certain amount of flow that goes through this impeller. Q is the flow that goes through this impeller, or flow of the liquid that is supplied to the eye of the impeller, and HP is the head that impeller is generating. Plot a relationship between this HP and Q. How will it look like? It will look something like this. When Q is 0, that HP is the maximum possible H head that impeller will generate. That's nothing but, if this is 0, it will be V tip square divided by G. Well, 1 second, let me just make that correction. Yeah, so the maximum head developed, that is when the flow is 0. When flow is 0, the maximum head that is developed is nothing but V tip square divided by G, or pi nd square divided by G. So maximum head is proportional to n square and d square. This is an important relationship. When HP is 0, when 0 head is developed, what we can do? Put 0 here. Then Q must be equal to V tip multiplied by AF multiplied by tan beta 2. And V tip is nothing but pi nd, and AF is again related to the radius or diameter of the impeller. And B, again, these are related to the size of the impeller. So when these impellers they are made in a geometrically similar manner. Means what? That all dimensions can be scaled by the same number for the same or the same value. So if radius is doubled, thickness also is doubled. So this distance that we called, this area that we called B, the width that we called B, that width is related to the diameter. So there is a diameter square dependence here, and there is one diameter dependence here and n dependence here. So that means the Q max is proportional to the speed of the impeller n multiplied by diameter cube of the impeller. This also is a very important relationship we should remember, right? So this is how a centrifugal pump works, how the head that the centrifugal pump develops, how it is related to the flow rate through the impeller. Let's go forward. Let's talk a little bit about this head and so on. So the delta P that it generates is proportional to HP multiplied by rho. Oops, there is a G term missing. Let me add that. Yeah, so the pressure that the impeller develops or pressure that the pump develops across the suction and discharge, that is related now to HP, the head that is added, multiplied by rho of the liquid or the fluid multiplied by G. So that's the delta P that it generates. Now this means that if I HP, remember HP is dependent on N and D. So for a given impeller and a given speed of rotation, N and D are fixed. So N square, D square are fixed. So instead of, suppose I have a pump, but instead of the pump, if a liquid coming in, suppose air goes into that pump, what will happen? This rho will drop very dramatically. If it was a liquid, rho would be 1000. And instead of that, if air goes in, this becomes now, let's say 1. So the pressure developed by the impeller, if it's a pump and if air goes in that pump, pressure developed by the impeller drops by a factor of 1000. So if increase in pressure was from 1 to 4, 3 atmospheres, it drops to 0.003 atmosphere. Now air cannot be transported by 0.003 atmosphere through that pipeline. Therefore, the centrifugal pump will not work if the impeller rotates in air or vapor. Now, there are two implications of that. First implication of that is that the centrifugal pump requires priming. Priming means you have to fill that pump with the liquid, with the water, with the liquid that is being sent. You have to fill that impeller completely with the liquid. Only then it will be able to generate the pressure difference that is required for making the liquid flow from one point to another point. That's the first point. That's called as priming. So centrifugal pumps require priming. And how priming is done? Let's say it's a water tank in our building. There is a foot wall that prevents, so when pump is stopped, the foot wall prevents the liquid from going down into the storage tank below. Or there are something called as self-priming pumps, or there are priming pots which are full of liquid, and when you start the pump, that liquid is filled in that pump. Liquid is always ensured that there is liquid in that pump. These are called as self-priming pots, and so that the pump is able to transfer liquid, because moment there is air or moment there is a vapor, the pressure developed will drop even if the head developed is the same. HP developed is the same whether it is rotating in air, vapor, or it is rotating in liquid, but pressure difference generated will depend on rho of the fluid that is inside. Second part or second important point of that is if the pressure at the suctions becomes low enough, then liquid will vaporize and you get a vapor. That's why it is important to ensure that the suction pressure is more than the vapor pressure by an amount which we call as net positive suction head, because impeller of a pump cannot work with vapors. The pressure developed will drop very, very dramatically. Second important point is third point, that is the second point. Second point was NPH. Third point arising out of this relationship is the difference between a pump and a blower or a compressor. Imagine that I have to increase the pressure of a liquid from 1 atmosphere to 4 atmosphere versus I have to increase pressure of a gas from 1 atmosphere to 4 atmosphere. Now density is, in one case, if it is liquid, is let's say like 1000. Okay, is let's say like 1000, and if it is a gas, let's say it is like 1. So if I have to increase pressure of a liquid by 3 atmosphere, from 1 atmosphere to 4 atmosphere, I will require a smaller n and d, because it is going to be multiplied by 1000, right? Whereas if it is a air that is being compressed from 1 atmosphere to 4 atmosphere, we will require n and d, which is much larger, because rho in that case is close to 1 or 2. So centrifugal blowers or centrifugal compressor will be much larger in size, diameter, and it will also rotate at a higher speed, much larger n. Okay. That's the third important point arising out of this. Let's go forward. This is again related to NPSH. Suppose we have a tank system like this. We want to transport water from, let's say, underground tank, or it can be a bore well, through this pump to an overhead tank, right? Now if I apply Bernoulli equation between 1 and 3, I will see that P3 by rho g is P atmospheric by rho g, pressure at 1, minus H1 minus H3 minus alpha 3 V3 square by 2g, minus head loss between 1 and 3. And you see this, now it has to pump higher. This height difference between 1 and 3, this height difference between 1 and 3 is getting subtracted from P atmosphere by rho g, subtracted. So if P atmosphere is 1, P atmosphere by rho g is typically 10 raised to 5 divided by 1000 divided by 10, right? Approximately P atmosphere divided by rho g is approximately 10. So this, if this height difference between 1 and 3 is like 9 meters, then I have only 1 meter of suction. 1 meter means 0.1 atmosphere, means 76 millimeters of mercury. Now it is approaching vapor pressure. So this liquid can vaporize, and if liquid vaporizes, again I cannot pump. That's why it is important to have pressure at 3 larger than vapor pressure by a minimum amount, which we call as net positive suction head. Pump manufacturer will tell us what this value should be. Accordingly, we have to decide what should be the location, where should I locate the pump. So if this is if let's say this difference is more than 10 meters, let's say it is 11 meters, now it will be 10 meters P atmosphere by rho g minus 11. Obviously pressure will become negative, obviously it will vaporize somewhere here itself before it goes into the pump itself, right? So now I should locate this pump lower and lower. So think what is done for bore wells. Find out for yourself, how do we do for bore well, where H1 minus H3 is typically very large. So bore well water, you get water maybe at 20 meters, 30 meters, 40 meters, and so on and so forth. Now how do I pump water? I can't have pump at the ground level because the suction head itself will not be enough. So then I have to locate the pump at lower and lower level. Just see what is done for bore wells, how pumps are designed for bore wells. Okay, now this characteristic that we had plotted, pump head versus flow characteristics, we had got this is a straight line between HP and Q. In reality, this is not a straight line. In reality, it is like this. This is the actual behavior, and this is because of the circulatory flow. Circulatory flow means circulatory flow between these blades. Fluid rotates between these blades. So there is a loss. There are vortices that form. So rather than going straight from entry to exit, it rotates. So there is a loss. Right? Second is because of friction. Right? Friction here. Friction for it to flow. Friction in the volute. Right? Third is that the guide vanes don't give perfect guidance. Means that fluid goes out at an angle not at beta but slightly less than beta. If it is slightly less than beta, or in this case slightly more towards the v omega, so it is actually not going like this, it is actually going like this. As a result, your tangential component is reduced, the head developed reduces. Or reverse flow. Reverse flow means, now you see pressure is, let's say if you look at the pressure is higher here, pressure is lower here. So rather than fluid going out, fluid might tend to go back into the impeller. That's called as a reverse flow. And as a result, if you have more and more viscous liquid, more recirculatory flow happens, more head is lost due to friction, and this characteristics actually drops. If the fluid viscosity increases, this curve actually goes like this, because friction is larger and larger. Guide vanes don't give that guidance. There is a reverse flow. So centrifugal pumps are not suitable for highly viscous liquids. Next point, this is HP versus Q. Can we plot power? What is power? Power is HP rho G and Q. So if you plot power versus flow rate, or efficiency, power delivered to the liquid divided by electrical power that is supplied to the motor, that will go through a maxima. Because somewhere here head is high but the flow rate is low. Somewhere here the flow is high but the head is low. So it goes through a maximum. So this point, if you plot in terms of efficiency, this point is called as the best efficiency point, and I would want to operate the pump at this point. I would want to operate this pump such that the head delivered by the pump is on this line. This is an ideal line, but actually I would want to operate it on this point here. I would want to ensure that the head that the pump develops and the flow that goes through the pump is corresponding to this point. I will choose a pump that will give me this flow and it will give me this head. Right? Okay, let's go forward. Okay, so here is a problem. So here is another problem that we have been doing. You want to transport water from here to here. Now you see, this is the actual behavior. This is like a parabolic equation. This is that parabolic equation that I gave you. Go back to that Bernoulli equation problem, Bernoulli equation lecture. This problem I had given to you. Okay. Now recall from there how we used to do. HP is H2 plus HF12. This is from that lecture only. Now these two things, the right side of the equation and the left side of the equation, look at that. This is proportional to Q. Right side is like this. This is the right side. Minimum is H2. This is minimum. H2 is not 0. Origin is it's not going through the origin. It's going through H2. Even when flow is 0, it has to develop this minimum head H2. And HF12, frictional head loss, we have seen it increases. So this curve is what the system requires. System means the piping requires. How much head the piping requires for a certain amount of flow Q to go through this pipe. That is given by this equation. That is what is plotted in this line. Whereas the pump is able to give me only this. If this much flow goes through, this much is the head developed. If this much flow goes through, this much is the head developed. So actual flow going through will be, either you can do it graphically, point of intersection, or by solving this equation that we have seen in our earlier class, right? and Q is in meter cube per hour. We have solved that. So that was the origin. So this is the origin for that problem. You might have wondered why I took head as some function of Q. This is the reason. This is the reason. This is the ideal. This is the actual. This is the actual. Okay. Some important time. So again, as I told you, pump manufacturers will make pumps which are geometrically similar, which means all dimensions are scaled up by some same amount. So radius is doubled, thickness is doubled, the width of the blade is doubled, radius of the blade is doubled, volute size is doubled. So these are called as geometrically similar. Now if I have to find out, if I have to do a problem, if I have to use a particular pump, I must know the head versus flow characteristics of the pump. The manufacturer is going to give me characteristics, but they are not going to give me characteristics of all kinds of pumps that I will require. So that's what they do is they make dimensionally similar pumps, and they measure the head versus flow characteristics of a small size by laboratory experiments. You will also do an experiment on measuring the actual head versus flow characteristics of a centrifugal pump. And then they tell you what is the head versus flow characteristics of a larger pump by looking at these dimensionless numbers. That's the advantage of these dimensionless numbers. Just like we have used friction factor versus Reynolds number, it's a dimensionless number, so that it is applicable across all pipe sizes, across all flow rates, across all types of fluids. So because the head is proportional to n square d square, we define a dimensionless number called as head number, which we define as G HP divided by n square d square. Because flow rate is proportional to n d cube, we make a dimensionless flow number nq as q divided by n cube. Sorry for the typing mistake here. So we define flow number as q divided by n d cube. And now you remember what is power? Power is HP rho g q. So HP I can replace from nh n square d square by g. Q I can replace as nq n d cube. Now I can rearrange this. Right? It will become n cube d raised to 5, and rho g will get cancelled out. So I can bring that on the other side. I can make a dimensionless number np power number as p divided by rho n cube d raised to 5, and that's nothing but nh multiplied by n cube. Now I can eliminate d between these two relationships, and I will get a relationship that looks like this. This also is a dimensionless number. We call this dimensionless number as specific speed. Okay, is nq raised to half divided by nh raised to 3 by 4. You can do this for yourself. You can check yourself. Okay. So this ns tells us something about how much is the head that impeller needs to generate and how much flow the impeller needs to generate. If the flow that impeller needs to generate is large, then these ns values are large. Then we go for what is called as axial flow pumps. If I need to generate large head, relatively small flow, then ns value is lower. That's typically centrifugal flow pumps. Now you can use these two. Again, these two relationships will tell you that if pumps are geometrically similar, then using one relationship for a small pump, I can always generate relationships for other diameter pumps operating at any other speed. Okay, we'll see a problem related to that now. So these are actual head flow relationships for a series of pump from a manufacturer. Actually, this data is from our White's book. Okay, you can see that for yourself. This 28-inch diameter impeller, 32-inch impeller diameter, 36 and 3/4 inch impeller diameter. Rotation speed is 1170 rpm. And these are the head flow characteristics. This is the head developed in feet. This is the flow in gallons per minute. So these pink lines are the head flow characteristics for different impellers, different sized impellers. You can see the diameter is increasing. These curves are shifting upwards. And these vertical lines are for different efficiency. So 65% efficiency, 72% efficiency, 78, 82, 85, 87, 88, and so on. And these are the different power that the fluid that the pump will require. 1500 brake horsepower means 1500 HP. 1500 HP is like 1000 kW. 2000 horsepower is like 1500 kW. 3000 horsepower is like 2100 kW. 3500 horsepower is like something like 2500 kW. Okay, so what is the best efficiency point for this case? The best efficiency point is somewhere here, 88%. For this impeller, the best efficiency point is somewhere here, 86%. For this impeller, the best efficiency point is somewhere here, it is 82, 83%. Okay, what I'm going to ask you to do is to find dimensionless numbers for these three impellers. Let's just take one as an example. You can do for the other two. So if you would say, let's just take 1 point on this 32-inch impeller diameter. It is operating at 1170 rpm. BP for 20,000 gallons per minute is and 380 feet head. So 20,000 gallons per minute. This is 20,000 gallons per minute. 20,000 gallons per minute, 32-inch. That is this point. This point will be the best efficiency point. That's the best efficiency point. Okay, you can calculate that for yourself. But right now, let's say this is the best efficiency point. Best efficiency point is 20,000 gallons per minute and a head of something like 380 feet. So 20,000 gallons per minute and 380 feet. Speed is 1170 rpm. 1170 rpm. Now convert that to revolutions per second. Divide by 60. Impeller diameter is 32 inch. Convert that to meters. Oops, this should be 0.813 meters, not millimeters. Let me just correct that. Right. So diameter is 0.813 meters, not millimeters. That correction I have made. Right, converted the diameter, converted the rpm, flow. So to 20,000 gallons per minute, you convert to meter cube per hour, meter cube per second if you like. That's the SI unit. And head, you convert 380 feet into, you will get 115 meters. And flow, if I convert 4,500 meter cube per hour, it is same as 1.25 meter cube per second. Now NH would be G multiplied by H. H is 115 G divided by N square, 19.5 square. It's a dimensionless number. So take care of units. 19.5 square, N square and D square, 0.813 square. You will get NH as 4.5. NQ will be 4,500 divided by, no, not 4,500. It will be 1.25 meter cube per second. SI unit. SI unit. It's a dimensionless number. 1.25 meter cube per second divided by N and diameter cube. That will give you 0.12. Specific speed, if we calculate, it will become 0.11. That will tell you type of impeller. Depending on the impeller type, specific speed will change. So if alternatively, if I know the specific speed, what specific speed I want, depending on how much flow and head I want, I can say, I will choose this type of impeller. Right now, let's not worry about that just now. Power number NH multiplied by NQ 0.55. Efficiency coming from here, we are at this point 20,000 and 380. Efficiency, this is 85%, this is 87%, so somewhere in between, typically 86%. So power delivered is 1450 kW. Power drawn is 1700 kW. It is 2200 HP. NPSH, you see the NPSH for this impeller? $30 like 9-10 meters, 9.1 meters, right? That means that's the NPSH that I want. Now I should arrange my piping and layout and location of the impeller such that this value that I get calculated from this suction pressure minus vapor pressure divided by rho g, this must be more than what the manufacturer is telling me to have. Manufacturer is telling me that it should have an NPSH of 30 feet. I need to arrange my piping and the layout so that the NPSH that I get available is more than the required. This is the required NPSH. Okay. Let's go forward. Okay, so the head flow characteristics of a centrifugal pump operating at 1440 RPM having a 25 centimeter diameter impeller are given here. HP versus Q. Oh, Q is not meter per hour, it is meter cube per hour. Let me make that correction. Okay, so flow is in meter cube per hour. Okay, so what you have to do, fit an expression of the type HP is equal to A minus B Q square, like what I had given you last time here, like this. This is of the type A, some constant, minus B Q square. So fit this relation, that's the first thing that we want to do. Fit this relationship. Oops, yeah. Calculate the dimensionless head versus flow characteristics of the pump, of this pump, NH versus NQ, you calculate. And then what would be the head versus flow characteristics of a geometrically scaled up pump? Geometrically scaled up pump with 50 centimeter diameter and 3000 RPM. So diameter is doubled, speed is approximately doubled, slightly more than doubled. Okay, do this problem for yourselves. Pause the video. Here's the answer. So what we will do, HP, we will find this is small p, HP, small a, capital H and small subscript p. So H we will give you, so let's pause, so many corrections are there, right? So calculate the NH values from the H values given. So from here, knowing N and D, diameter and speed, diameter is 0.25 meters and speed is 1440 RPM, which means 24 RPS. So 24 RPS, revolutions per second. Remember, it's a dimensionless number. We have to take care of units. And diameter is 0.25 meters. So NH would be this head multiplied by 9.81 divided by 0.25 square and 24 square. Same way Q is meter cube per hour. If you divide by 3600, you will get meter cube per second. Then you will have to divide by N, 24, and diameter cube, 0.25 cube. That's how you will get the NQ values. Now using this NH and NP values, now if the pumps are geometrically similar, then that means the NH and NQ relationship remains the same for a bigger impeller as well, a bigger pump as well. So now using this for a bigger impeller is 50 centimeter diameter, means 0.5 meter diameter, and 50 RPS, 3000 RPM, so 50 RPS. This is 50, it should look like 50 RPS, right? So using this NH, you can calculate head for a bigger pump. From here, how will you get this? This multiplied by n square d square divided by g. N is 50 square, d is 0.5 square divided by g, you will get the head. Same way from the NQ, how will you get the flow rate? Q is NQ multiplied by n d cube. N is 50 RPS, Q d is 0.5 meters cube, that you will get flow rate in meter cube per second multiplied by 3600, you will get it in meter cube per hour. So that's how manufacturer also will do. Manufacturer will measure the head flow for a small pump in a laboratory or in his workshop or in his factory, and then he will give you these characteristics for whatever diameter, impeller, speed you want for whatever application. Okay, one last point is a positive displacement pump. So positive displacement pump, remember I told you the flow rate that it generates will be decided by how much is the stroke length and the frequency, how many times it is doing that stroke per minute. That will decide the flow rate. So flow rate is fixed irrespective of the discharge pressure, means irrespective of the head, the flow rate is practically constant. So the head versus flow characteristics for a centrifugal, for a positive displacement pump is like a vertical line. That's why for highly viscous liquids where the head versus flow characteristics dramatically drop for a centrifugal pump, it is ideally suited for handling highly viscous liquids, positive displacement kind of pumps. Our heart also is a positive displacement pump because our demand of the blood in different parts of the body is practically fixed. The body has to pump 5 liters per minute irrespective of the head, means irrespective of how much cholesterol is there, what is the friction in the artery, and so on and so forth. Even the artery is narrowed, frictional head loss increases, heart has to give higher head. But because it's a positive displacement, depending on how many times it beats and what is the volume of the chamber in the heart, it will pump that much amount of blood all the time, every time, irrespective of whether artery is clean or artery is clogged with cholesterol. That's why it is a positive displacement pump, and that's why we don't realize that the arteries are blocked. The blood is going at the same rate all the time, whether artery is clean or artery is partly blocked. The flow is the same. Blood reaches the body parts at the same rate. People don't realize, but heart has to do more pumping action. Head, it has to supply more, and therefore the muscles wear out. That's why heart attacks are a silent killer. You don't see the effects. You only don't see it even till the last moment. The flow rate is the same. No matter how much extra head the heart has to supply to overcome friction in the arteries. That's why heart is a positive displacement pump. We could not have heart as a centrifugal pump, because moment head increases, the flow rate drops dramatically. And if flow rate drops dramatically, we would have felt it by tingling sensation, giddiness, all those things. So you see, our hearts are nice positive displacement pumps, and therefore we don't realize that they are that any problem is created even when the arteries are narrowed down. Okay, that's what I wanted to cover in this part of the lecture. So you should be able to do all these problems now, and we have seen very much in detail how the centrifugal pump works, how the head versus flow characteristics are for a centrifugal pump. And in the next class we'll talk very briefly about uh, compressors, how what do we do for compressing gases, for supplying gases at a higher pressure. So that's coming in the next class.